Let's study Newton's laws of motion using an inquiry-based approach. So we'll be answering a series of questions for us to understand the topic. Newton's first law, it states that an object at rest tends to stay at rest, and an object in motion tends to stay in motion unless acted upon by an unbalanced force. What is meant by an unbalanced force? A physics book placed on top of a table. So the situation shows forces that are balanced each other. You have the table pushes upward force on the book, and the force of gravity pulls downward on the book. If forces on an object are equal and opposite, they are said to be balanced, and the object experiences no change in motion. If they are not equal and opposite, then the forces are unbalanced, and the motion of the object changes. So what is the consequence of balanced forces? So meaning if all the summation of forces acting on the body equals 0, or if net is equal to 0, then an object in motion tends to stay in motion, and an object at rest tends to stay at rest unless there is an unbalanced force. So this is Newton's first law. Further, if summation of force along x is equal to 0, then there is no possible change of motion along horizontal. And also, if the summation of force along y is also equal to 0, there is no possible change of the state of motion either at rest or constant speed along vertical axis. And then y first law is also called the law of inertia. By definition, inertia is the tendency of an object to resist changes in its state of motion. This is just the restatement of the first law, that object at rest will continue to stay at rest, and if it is moving, it will continue to have a constant velocity, meaning it's just the resistance of the change of its state of motion. And then first law states that all objects have inertia. The more mass an object has, the greater its inertia, and therefore it is harder to change its motion if it is very massive. If objects in motion tend to stay in motion, why don't moving objects keep moving forever? Actually, things don't keep moving forever because there's almost always an unbalanced force acting upon it. For example, this book sliding across a table slows down and stops because of the force of friction. And the force of friction is one sample of an unbalanced force. Another, if you throw a ball upwards, it will eventually slow down and fall because of the force of gravity, which is also the unbalanced force in this case. In Newton's second law, we have in here the unbalanced force. And this unbalanced force, or if net, equals mass times the acceleration. And acceleration, by definition, it is a measurement of how quickly an object is changing its velocity. What do you mean by if net equals ma? It means that the unbalanced external force is directly proportional to mass and its acceleration. So, a ball of a certain mass moving at a certain acceleration, this ball is being acted by an unbalanced force. So, if another ball twice as big, meaning you double the mass, but has the same acceleration with the first ball, meaning m2 is equal to 2m1, first ball, then f2 should be twice of your F1. It means that the second ball has twice the force of the first ball. And if the first ball moving twice the original acceleration, then F is equal to ma says that the ball will again have twice the force of the ball at the original acceleration. So meaning, if you double the mass, you double the force. And if you double the acceleration, you need to double the force. The equation if net is equal to ma will have these consequences. Like this, something very massive, meaning high mass, like a glacier, that's changing in speed very slowly, meaning low acceleration, can still have a greater force. Likewise, something very small, low mass, that's changing speed very quickly, meaning high in acceleration, like this bullet, can still have a great force because of this equation. For Newton's third law, it says that for every action, there is an equal and opposite reaction always. So meaning forces come in pairs. Let's have an activity to illustrate this concept. A perfect drop shot. So in this activity, you need to identify the Newton's laws of motion as demonstrated. So we have the materials, the bottle, plastic ring, and chalk prepared in this setup as shown in the picture. In this activity, you have to hit the ring as quick as possible in order for the chalk to fall directly inside the bottle. And then you do this at home. And then from among many attempts, you have to answer this question. What settings must be considered in making a successful drop shot? And then answer why. And number 2, in what part of the ring, when smashed, would give a possible successful drop shot and why? This time, let's identify all the forces acting on the specific body. Example, the chalk at rest on top of the ring. We have in here directed upward force by the ring on the chalk and, of course, the force of gravity on the chalk. And how about the chalk while falling down the bottle? So the chalk will be acted only by the force of gravity and nothing else. How about the ring at the top of the bottle with a chalk on top of it? Now, our body is the ring. So what are the forces acting on the ring? So of course, the force of bottle on the ring, this one, the force upward. And the weight of the chalk on top of the ring. Another, the force of gravity on the ring. So we have two forces acting downwards at an instant when the ring was hit. This time, our body is the ring. So we have in here the force of bottle on the ring. The force is directed upward. And the force exerted by the hand horizontal, either in this direction or that direction. And also, the weight of the chalk is also exerting on top of the ring, plus the force of gravity on the ring, which is equivalent to the weight of the ring. So in this setup, we disregard the effect of friction. So for question number 4, let's identify first law in the setup and explain why it is first law. So first law is portrayed in the following. 1. The chalk at rest on top of the ring. All the forces acting on the chalk balance each other. Therefore, if net is equal to 0. Another, the ring at rest on top of the bottle while the chalk was on top of it. Again, in this setup, the sum of all the forces acting on the ring is equal to 0. So what part of the activity demonstrated the law of inertia and why it is inertia? The law of inertia was demonstrated in the resistance of the chalk to change its state of being at rest when the ring under it was snappishly removed. So the law of inertia is defined as the tendency of the body to resist change in its state of motion. So the reason why the chalk would just free fall towards the bottle. For question number 6, pinpoint parts of the activity which demonstrated the second law. And why do you think it's the second law? So we have in here the chalk falling down, simply falling down towards the mouth of the bottle after the ring was quickly removed. So the net force on the chalk is equal to its weight. So thus it accelerates with acceleration due to gravity. So we have in here summation of force along y is equal to ma, or a, which is equal to the acceleration due to gravity, so downwards. Another second law is when the ring hit by the hand. So the vertical component of the force acting on the ring balance each other. The force of battle on the ring, the weight of the chalk plus the weight of the gravity on the ring downward. This balance the force on the ring. But you have the horizontal force, which is unbalanced, equal to the force exerted by the hand in removing quickly the ring. So this is now our if net, which demonstrated the second law. This now will accelerate the ring horizontally. This time, let's identify the third law in the system, or the action and reaction pair of forces. Let's start with this interaction, the two-body system. Take note, in the third law, we're talking two-body system. Sample the chalk and the ring. So we have force of the ring on the chalk, which is upward, and the force of the chalk on the ring. So this is ring on chalk and chalk on ring. So these are sample of interacting forces. Another, we have the ring and bottle. The force of the bottle on the ring and also the force of the ring on the bottle. And we also have the ring and earth. So the force of the ring on earth and also the force of earth on ring. Another interacting forces, or the pair of forces. We have the force of chalk on earth and also the pull of the earth on chalk. So what have you noticed? Pair of forces are forces exerted by two bodies. So that's why it's a two-body system. So after performing the activity, I think you can answer now the first two questions. So first question, from among many attempts, what settings must be considered in making a successful drop shot and why? So maybe you conclude that the hand direction in hitting the ring should be horizontal to avoid possible upward force applied on the chalk. Another thing to consider, the finger or your hand must touch only at the inner part of the ring, not on the outer part, to avoid vertical deformation of the ring. And then the hit must be quick enough in order that the chalk has the tendency to stay horizontally at rest after the ring flew off. Right? And for number 2 question, in what part of the ring when smashed would give a possible successful drop shot and why? It should be only in the inner mid-horizontal portion, inner, this direction, and only in the inside. Other parts, when hit, may cause deformation of the ring resulting to a net force applied on the chalk, other than the force of gravity that would make the chalk to fall down. So it's your turn, your assignment. You have to perform the activity, the ring chalk or the perfect drop shot activity at home. And then you're going to answer also these questions. Will the ball continue to stay in the line forever? If yes, how and why? Are there forces acting on the ball? If yes, identify these forces. Is force necessary to keep the ball at rest? Generally, what causes the body to change its state of rest or in motion? Another set of questions referring to the picture above. What are the forces acting on the rolling ball? And what makes the ball slow down on its own? And is force necessary to keep the ball rolling? Then why? In our next session, let's apply Newton's laws of motion in a specific problem.